All right. Very good afternoon to everybody. I hope that everybody enjoyed today's lunch. At least I did. I think that quite a number of varieties for us to choose. All right. So thank you so much for coming to this session on the 3D displays and rendering. And just to share with you, there is 1 hour for this session, and we have 4 papers to present. Before we invite the first presenter to present the research, just to see a few words about how this session is organized. So each paper will have 15 minutes in total. That includes 12 minutes for presentation, times 3 minutes for Q&A. So I will have a time watcher here. So when it comes to 10 minutes, I just will ring the bell 1 time. When it comes to 12 minutes, I will just press the bell for twice. Okay, so which means that you need to finish your presentation soonest. All right. So yeah, we are just on time. Without further ado, let's welcome the first presenter, Andy. Yeah, Andy, I think the floor is yours now. Yeah.
Thank you. Then, yeah, okay. Hello, everyone, and welcome to my presentation on virtual pass-through evaluating 3D Gaussian splitting as an alternative to conventional video pass-through in static environments. My name is Andy Schleising, and this work was conducted together with my colleagues Christian Kühnert, Tobias Schwand, and Wolfgang Proll as a part of our research on extended reality and novel scene representation. Let's start with a short introduction and the motivation behind our work. Video pass-through, or VPT, means that the user perceives the real environment without the headset's camera displayed almost one-to-one inside the headset. However, VPT is still affected by optical distortions, such as bevel or pincushion distortions, which can alter how depth and geometry are perceived. In contrast, 3D Gaussian splatting, or 3DGS, is an emergent nerve-based rendering technique that reconstructs and renders scenes from captured data. It achieves almost photorealistic results, including lighting and shadow details, without relying on the physical camera feed. This observation motivated us to think about how these two visualization methods might differ in terms of user experience, and ultimately lead us to define our research question. So, building on these considerations, we formulate 3 research questions for our study. First, we want to know whether the perceived realism differs between 3DGS and conventional VPT, visualization of the same XR scene. Second, we asked how the type of visualization, 3DGS versus VPT, might influence the user sense of spatial presence in XR environments. And third, we examined whether 3DGS visualizations reduce perceived visual distortions, such as rendering artifacts or the well-known telescope eye effect, comparing to conventional VPT. Together, all these questions guided the design and analysis of our user study, which I'll introduce next. To create our dataset, we captured several scenes using our IRC framework in combination with an iPhone 16 and focused orbit capturing with 3 circular layers, what you can see in the video, and different viewing angles around the object. This approach provides for us the most complete and stable reconstruction for the 3DGS pipeline. Here you can see the training outcomes for each of the three scenes. High detailed as Lego, natural depth as plant, and reflection surfaces as water. Using the original 3DGS implementation by Kerbal et al., the table compares 2 training stages, 7,000 and 30,000 iterations. As expected, all scenes show clear improvement in PSNR and L1 matrix over time, indicating better reconstruction quality. Notably, all final models trained for 30,000 iterations achieve PSNR value above 30, which represent a very good visual fidelity for static XR scenes. So here you can see the final reconstruction for the 3D scene after the training and the fine tuning. We remove all floating artifacts, also called floaters, to achieve a clean and stable visualization. These three examples, Lego, plant, and water, represent the final versions used in our user study. Before we start the actual experiment, each participant completed a short tutorial session. In this tutorial, they were shown a neutral scene, just an empty table in both VBT and 3DGS for 30 seconds each. This familiarization phase helped participants understand how the two visualization types look and behave and allowed them to adjust their HMD. After that, we conducted them the main within subject explorative study with 18 participants. Each participant experienced all three scenes, both in VPT and in 3DGS, present in balanced Latin square order to control the sequence effects. The study was conducted using a MetaQuest 3 and is connected via a MetaQuest link running on our XR prototype in Unity, what was on a laptop. Finally, after completing all tries, participants provide an overall perceiving rating, indicating which visualization they perceived as more realistic and comfortable. And here in the video, you can see how the behavior was for the users. So, in this slide, shows a simplified overview for the scenes that participants viewing during the study, presented in direct comparison. On the top left image, you can see the 3DGS scene, while the bottom right image shows the corresponding VBT scene. This short study was conducted in 3 phases. The first phase, shown in orange, followed the balanced Latin square order. In this phase, participants viewed each scene either in VBT and 3DGS, following by completing the IPQ questionnaire. In this phase, listed 45 seconds per visualization. The second phase, marked in green, allowed participants to compare both visualization directly, VBT and 3DGS, with the option to remove the HMD and observe the both representations side by side. The comparison phase lasted up to 2 minutes. Finally, the third phase, highlighting in blue, consistently of a custom question in which participants were asked to make a final decision, which visualization they preferred overall. Here you can see the box plot visualization about the IPQ questionnaire for all dimensions of the IPQ across all 3 scenes. The orange boxes represent VBT and the blue boxes represent 3DGS. As the plots show, VBT generally receive higher median ratings, particularly for spatial presence, realism, and the overall presence score. The involvement shows scores, however, remain relatively similar between both visualization types, showing no clear trend. What's interesting is that despite 3DGS offers a more reconstructed environment, users still reported a slightly stronger feeling of presence in the real camera-based VBT condition. So let's take a look to the custom question on perceiving distortions. For each scene, we compared how often participants reported visual distortions in VBT versus 3DGS. As shown in the table, only the plant scene revealed a significant difference, where participants reported more distortion in VBT conditions. For the Lego and the water scenes, differences were no significant. However, when we aggregate all distortion reports across all scenes and applied an exact McNamara test, the overall result was statistically significant. That means, in general, participants were significantly more likely to perceive distortions in the VBT condition comparing to 3DGS. The next one measures focus on perceived object closeness. In other words, how close or far away was the object apparent to the user in each visualization type. The table shows the results for all 3 scenes based on the Wilcoxon sign and rank test. We found a significant difference only in the LEGO scene, where participants perceived the object as closer in the 3DGS condition than in VBT. For the plant and water scenes, no significant difference was observed, although 3DGS again tended to produce slightly higher proximity ratings. When aggregating all scenes, no consistently effect was found. So the next one was focused on perceived object quality. That is how visual enhanced or realistic the object appears to the participants. In the LEGO scene, no statistically significant difference was found, although 3DGS received slightly higher ratings overall. In the plant scene, the results were again no significant, and the ratings between 3DGS and VBT were quite similar. However, in the water scene, we observe a significant effect, with higher ratings for VBT. This suggests that the real video capturing of dynamic water might have been perceived as more visually convinced than in the 3DGS reconstruction. When aggregating responses across all scenes, the difference was not significant, indicating overall comparable visual quality between both conditions. In summary, while the difference in perceived object quality was not dramatically, the results indicates that VBT have an advantage in scenes with dynamic effects such as water. Conversely, 3DGS performed equal well or slightly better in artificial structured environments like the LEGO scene. These findings highlight that the type of scene content plays an important role when selecting a visual methods for XR application. Finally, participants were asked visual types preferred overall. VBT and 3DGS for each of the three scenes. As shown in the table, the preferences were relatively balanced across all scenes. This suggests that the scene content rather than the visualization method itself may play a more decisive role in shaping the user preference. So, to the conclusion, our research shown several key insights. First, participants report fewer visual distortion in 3DGS to visual pass-through. This indicates that for static scenes, 3DGS can serve a available rendering alternative for XR application. Second, users generally accept 3DGS scenes well, showing that even though the environment is reconstructed rather than live, it's still natural and believable. However, for dynamic content such as moving elements or complex lighting, VBT still have an advantage because it reflects real-world motion and illumination directly. Overall, our findings suggest that 3DGS can indeed be integrated into XR contexts, but its effectiveness strongly depends on the type of the scene and the quality of the captured process. As noted, under our limitation, achieved high-quality results require fully captured scenes and stable data. In summary, our research question 3, focusing on distortion, can be clearly answered. 3DGS showed fewer distortion than VBT. Our research question 1 and 2, related to realism and spatial presence, showed only weak indicators, suggesting that future research and larger scale studies are needed to confirm these trends. Thank you very much.
Yeah. Very good timing, just exactly 12 minutes. Okay, so maybe open the mic for any question, please. Oh, yes, please.
Thank you. Were the participants notified about the differences of these two conditions? The intention of the question is, if you only experience the Gaussian splatting condition, can people realize it's a recorded one immediately, or maybe it will take a while for them to notice?
Thank you for the question. Overall, it was not depends on the scene. because we have also a limitation in our scene that the 3D GS scene is like a VR scene. That means we have not captured the whole room, but more like the table. And that means if the people look to your hands, because we have no hand inclusion included, they know, okay, that's not real. And also if they're looking to the top or to the surroundings about the table, they saw it. But we also saw that in the water scene and the plant scene, it was not directly notable for the users and also for the Lego scene, but that is, I cannot clearly say yes or no, because we have this limitation that if the people look around, they know it, okay, it's not real. I hope that answers your question. Okay.
All right, great. I think that due to the time consideration, maybe we invite the second presenter to be on stage. And thanks a lot to Andy again for the presentation. If you have any questions, just after this session, just come to Andy for further discussion. Thank you.
Okay. Good afternoon, everyone. My name is Xiaodan Hu from Grass University of Technology. Today, I'd like to introduce our work on XMask improving soft edge occlusion in optical scissor displays with cloth-shaped pinholes. And this work is a collaboration work between Grass University of Technology, Shanghai Jiao Tong University, and another Institute of Science and Technology. When we look through a conventional optical scissor display, virtual objects often appear semi-transparent, like this red teapot. That is because real-world light is still reaching our eyes through the light combiners such as half mirrors. And this breaks immersion, reduces depth cues, and makes virtual objects float unnaturally. To solve this, we add an occlusion mask, a dark region that physically blocks incoming light exactly when where the virtual object is located. With this mask in place, the transparent teapot now becomes a solid red teapot. It looks physically present in the scene with proper depth cues and no longer float like a ghost. To physically block ambient light, we typically use a spatial light modulator, such as a transparent LCD, to generate an occlusion mask. If we simply place the LCD in front of the eyes, it becomes the most straightforward occlusion method. However, because our eyes cannot focus on both the distant scene and the LCD at the same time, the occlusion mask appear blurred. We call it soft edge occlusion, and it's compact but blurry. To make both scene and the occlusion mask sharp, we need to add several optical elements to align the focal planes. This configuration produces hard edge occlusion, which is sharp but requires a bulky optical setup. So we started to think, how can we keep the occlusion mask sharp but reduce the form factor of the system? Our approach is to use a pinhole array. We know that a pinhole camera with its very small aperture can keep everything all in focus. Just like a nearsighted person can see more clearly by squinting their eyes, which effectively create a smaller aperture. So if we place a pinhole between eyes and occlusion mask, we can keep both mask and scene sharp. However, if we only have one pinhole, very little light can pass through. So the image becomes very dark. To make the image brighter, we use multiple pinholes, forming a pinhole array. But with multiple pinholes, each pinhole captures a slightly different view of the scene, so the image becomes split. To fix this, we need to generate elemental images. While each small image corresponds to one pinhole, when all these elemental images pass through their respective pinholes, they recombine into a complete bright image on the retina. These ideas come from our previous work, which was presented in the poster track at HBO UVR 2024, where we implemented both a pinhole array and occlusion mask using two transparent LCD panels. On the right, you can see the effect of seeing through a pinhole array. Notice that the distinct text and the near occlusion mask AR are both sharp. That is good part. But if you look closely, the image look kind of dirty. So you can see overlapping circles across the view. And these circles are the defocus image of the pinhole itself. Because the pinhole array is close to the eye, it's out of focus. So each pinhole produces a blur circle. Where this circle overlap, the brightness adds up and become brighter. So even though the mask is sharper, we get non-uniform brightness and distorted contrast. These are the artifacts we need to adjust. Now, let's think about why those blurred pinholes appear that way. The blur we see is actually the convolution of the pinhole pattern and the pupil aperture. For example, if the pinhole size is about 1 millimeter and the pupil size is about 4 millimeter, the convolution result is still become a circle, even if we change the pinhole shape to a square. That's because the pupil is too large and dominates the blur. However, circle cannot tell the plane seamlessly, which is why in the previous slide you saw overlapping circles. So we start thinking, what kind of shapes can tell seamlessly? Shapes like squares and hexagons can. Interestingly, when we convert clock-shaped pinhole and the star-shaped pinholes with circular pupil, the resulting blur naturally forms square-like or hexagon-like patterns. That's the key behind our X-mask design. Now we need to design the pinhole pattern. In general, when the line length of the cloth is about the same as the pupil diameter, the resulting blur pattern becomes almost a perfect square. Also, you can still see a very light semicircular on each side of the square. If the line length is shorter than the pupil diameter, the blur pattern becomes more circular. In contrast, when the line length is longer, the blur patterns gradually approach to the original pinhole shape, like a cloth. We also analyze the relationship between line length and the squareness through simulation. We use a solver operator to extract the contour of the blur. You can see the rate of change. The rate of change in squareness become very small. Here become very small, which gives up a wide design tolerance for practical implementation. Next, we need to design the elemental occlusion mask. If we consider a single circular pinhole, only in the area inside the yellow circle D can be seen through the pinhole. When we switch to a cloud-shaped pinhole, the visible region becomes this cloud shape. And this shape is actually the result of convolution of the cloud pinhole and the disk D. So it represents all the lines can pass through both the pinhole and the pupil. And more light pass through near the center and the less light pass through near the edge. The circular or this cloud-like region can be regarded as the elemental mask area. Now, if we have two pinholes side by side, their visible regions, these cloud-shaped areas start to overlap. So it's impossible to generate the precise elemental mask for each pinhole. So based on a geometric relationship, we simplify each elemental region into a square area instead. This introduces a little crosstalk because light from this overlapping area will pass through both pinholes. But it allows us to successfully reconstruct the original occlusion marks on the retina. And as I mentioned, less light pass through near the edge, which also this overlapping area. So the crosstalk remains within an acceptable range. Then we simulated our display in Unity to verify the visual effect and also to determine the optimal pinhole layout. We place our setup in front of a rendered scene and added virtual contents. The pupil size is set to almost 4 millimeters and focusing at 1 meter away. To make it realistic, the virtual contents were set to be only 1/3 the brightness of the real-world background. Because the background is much brighter, the PSNR and SSIM value, you can see for without pinhole case and our method looks quite similar. However, our method still shows a slightly better result overall. And if we remove the background like these two images, and only compare the occlusion mask, the difference become clearly. Our method produces a sharper mask. Also, you can notice some minor artifacts in the background. And here are our experiment set up to have the real see-through view. Similar to our previous work, we use two transparent LCD to produce both pinhole array and occlusion mask. But here we also add a burst path structure, a simple burst path structure to produce a virtual content. And in the middle, this is a cross-shaped pinhole array pattern, and this is the elemental masks. And here are the see-through results captured by a camera with about a 4 millimeter aperture focusing at 2 meters. So in the first column, without pinholes, the occlusion mask is obviously blurry, and that is the typical soft edge problem. So when we add circular pinholes, the mask becomes sharper. But you can also clearly see this dark diamond region, which has gaps between the defocus pinhole. With our method using cross-shaped pinholes, the artifacts are much less noticeable. And if the black background is not white, these artifacts become even harder to notice. So let's look at the see-through result with the virtual image added. Without the pinhole, yes, this is the soft edge occlusion, the virtual image appears semi-transparent because the occlusion margin is too blurry to fully block the background light. With circular pinholes, you can still see this diamond-shaped gap. And in contrast, our methods, the slight blur from the overlapping regions becomes much less noticeable once the virtual image is added, because the mask now blocks enough incoming light. The virtual object looks solid, and the background is also more uniform. Finally, let's talk about the limitation and the future potential. Obviously, the key limitation is the crosstalk, which makes the occlusion mask appear slightly blurry. The brightness is also relatively low because we use two transparent LCD panels and together with the polarizer blocks a significant amount of incoming light. And in addition, transparent LCD also introduce diffraction. For future work, since both pinhole and the mask are rendered on LCDs, they are fully dynamic. That means we can integrate gaze contingent feature, which allows the pinhole layout to adapt in real time to eye position and the pupil size. Moreover, human visual perception is often more tolerant to blur than what we see in the photographs. This suggests that in actual use, these artifacts might appear much less noticeable, which is something we plan to investigate further in the future. To summarize, we propose XMask lensless occlusion system using cross-shaped pinholes and produce sharper occlusion edges and more uniform retinal tiling compared to conventional method. And we validate the design through both simulation and the physical prototype, and showing that effectively improve occlusion quality while remain lightweight and practical for OST HMDs. And that is all for my presentation. Thank you for your attention.
Thank you, Xiaodan. Any question? Oh.
Hi, Shohei Mori from University of Stuttgart. So actually, the question, the limitations I wanted to mention has been already covered in your slides, but do you think, let's say, either of them can be resolved in a realistic way? I mean, for example, the diffractions
Yes,
or like compactness and everything.
yes.
Which one is the most feasible, how can I say, addressable limitations you think?
Which one is the most adjustable limitation? So now we have three limitations. I think diffraction, yes, diffraction is common in transparent LCD. If we use transparent LCD, use this device, we must have deep diffraction. So we to overcome this, we have to use another materials like photochromic materials like this. But still, it cannot. It's hard to control. So I think the maybe it's the low brightness. Yeah, yes, because now currently the transparent LCD we use are very old. So I think nowadays with new technology we can have some a transparent LCD with higher transmittance, and that may improve the brightness.
Okay, thanks.
Do we have another question? Yeah, maybe if no question, maybe I'll just a very quick one. So what is the size in terms of the thickness of your occlusion device?
Yes. What is?
What the thickness? You know, you have the pinhole plane, you have
Yes.
the LCD, right?
Yes.
What is the distance between?
Yes. The distance is about 4 centimeters.
4 centimeters.
Yes.
So which means that let's say if I wear an air glass, so in order to achieve this occlusion, I need to
Yes.
have another 4 centimeters kind
Yes.
of a mask.
But why we have 4 centimeters? That is because the transparent LCD, as I said, is a very old device. The
Okay.
contrast of transparent LCD is very low.
All right. Okay.
Yeah, if we have a higher contrast and smaller pixel pitch, we can reduce the distance.
Yeah. Thank you so much. Okay. Thank you once again. Thank you.
Good afternoon. I'm Diana from Metri. I will present our work on enhanced adaptive subdivision for dynamic mesh compression to improve visual quality. I will start with background and VDMC overview, then our two approaches and results, and close with limitation and future work. Mesh remains central in XR because they integrate well with modeling, animation, and rendering, and are broadly supported by engines and tools. New or hybrid representation are progressing, but meshes still remain practical for real product. Dynamic meshes are heavy. Dynamic mesh compression aims to reduce bandwidth and storage, preserving visual quality to make streaming or interactive XR service more feasible. Dynamic mesh compression have been standardized through VDMC, short for video-based dynamic mesh coding. VDMC build on proven video coding tool like HVC or VVC, which make it efficient, hardware accelerated, and practical for deployment. However, the preserving visual fidelity and low bitrate remains still challenging. VDMC split the data into 4 components: base mesh, displacement, texture, and atlas. One of the key features is separating geometry into base mesh plus displacement to reduce the geometry data size and support the scalable reconstruction across LOD. Let's just see how geometry is reconstructed in VDMC. At first, the original mesh is simplified into base mesh, and then it is subdivided across level of detail. The displacement is defined as the residual between subdivided base mesh and the original mesh. At the decoder side, the final geometry is reconstructed by adding displacement back to the subdivided base mesh. Subdivision increases resolution of mesh by inserting new vertices. The tool is controlled by subdivision scheme, iteration count, and adherence threshold. Each subdivision iteration apply two-step vertex position update and face and edge update. For vertex position update, subdivision schemes such as midpoint, loop, normal, and bisect can be applied to update the vertex position. Midpoint preserve the original shape of a mesh, while loop produces a smoother surface. For face and edge update, subdivision can be either uniform or adaptive. In adaptive subdivision, only edge longer than given threshold are split. Subdivision is primary control because subdivision directly affect both bitrate and quality. At typical bitrate, around 3 to 25 megabps, VDMC achieve very high compression performance. However, the fine geometric details often not fully recovered and small visual artifacts appear. That mainly come from strong decimation at the start. And subdivision should help to mitigate this artifact, but in its current form, it is rather rigid and inflexible. We believe this observation point to two notable limitations of subdivision within VDMC. First limitation is adaptive face and edge update. From here, I will refer this tool simply as adaptive subdivision. The tool is designed to control face count and bitrate, but it works only with midpoint across all LOD, so flexibility remains limited. Second limitation is lack of outlier handling. The outlier is a few polygon crossed by decimation, such as bow tie or degenerated triangle. But these outlier can be easily distorted when smoothing subdivision scheme is applied. However, in the current VDMC lacks systematic detection or handling to prevent distortion from outliers. These two issues motivate our approaches. I will present two complementary ideas. Approach one addresses the rigidity of adaptive subdivision, and approach two deal with lack of outlier handling. We aim to make a current subdivision of VDMC more reliable and more feasible. Approach one focuses on limitation one. The current subdivision, in the current VDMC, the adaptive subdivision work only when midpoint is applied across all LOD. But approach one removes this constraint which allows adaptive subdivision work with any scheme. That means the tool is activated whenever the adherence threshold is greater than 0, regardless of scheme. Let's see how approach one enables a subdivision scheme selection across the level of detail. The key is each LOD has different priorities. So the same subdivision scheme should not be applied at every level. In other words, we have to apply subdivision scheme hierarchically across reconstruction levels. At the early LODs, the mesh is very coarse, and every vertex carries important structural information. At this stage, shape preserving scheme like midpoint can help to preserve initial shape. At the early LOD, the mesh becomes denser, and smoothing scheme like a loop can be useful to reduce the bitrate and improve visual quality while still maintaining overall structure. The key takeaway is to apply appropriate combination of shape preserving and smoothing scheme across LOD. On our observation, the middle loop is often favored for natural visuals, while middle loop is often favored for objective coding gain. The choice depends on the application goal. Earlier, I proposed to apply a combination of smoothing and shape preserve scheme, but smoothing scheme have also drawback. The smoothing scheme can erode fine details, so outlier like bow tie or degenerated triangle can be distorted when smoothing scheme is applied. So the fragile or sensitive region need to be protected from unwanted deformation. This brings us to approach 2. Approach 2 classify vertex into regular, outlier, and very sharp, and determine the subdivision scheme for each vertex based on its classification. For outlier or sharp vertex, shape preserving scheme is applied, and for regular vertex, we allow flexible scheme application. This shows how approach 2 extends the workflow of approach 1. The newly added step is highlighted in red, and the approach 2 consists of 3 steps. The first, it detects outlier vertex, and for non-outlier region, it evaluates local surface sharpness based on similarity of a normal vector of adjacent triangle around the current vertex. Then suitable subdivision scheme is assigned. The approach 2 aims to make approach 1 more reliable while maintaining its efficiency benefit. Before reporting experimental result, I will share the setup. The baseline software is VGMC test model with adaptive subdivision. We run 2 comparisons, anchor versus approach 1 and anchor versus approach 1 combined with approach 2. For encoder parameter, subdivision iteration count was fixed at 3 and adherence threshold was set to 5. Anchor use midpoint only while approach 1 use mid-loop as representative combination. We use bit rate on 2 metric families, point-based for surface samples and image-based for multiple renders. Together, they reflect both accuracy and efficiency. Let's see objective code evaluation result. For test 1, which evaluates approach 1, we can see bit rate gain of about 2 to 6%. These mainly come from 2 factors: smaller displacement stream and slightly higher geometry PSNR. For test 2, which validate approach 1 and 2 together, we can see comparable or slightly higher coding gain compared with test 1. That means approach 2 preserve efficiency benefit of approach 1 while reducing outlier-driven distortion. The robustness does not fully appear in the numbers here, but it becomes clearer in subjective evaluation. Earlier, we used mid loop as representative setting, but our proposals support other mixes like mid-loop. For subjective evaluation, I will show the result for both. The first column show raw input data. Second column show anchors result. Column 3 and 4 show result obtained by our approaches. Mid-loop use loop more often. The surface look smoother than mid-loop. Both results look closer to the original than anchors result. On another test sequence, we can see artifact around the eye and cheek was noticeably suppressed. This is side-by-side video comparison. We believe our method helped to reduce geometry jitter over time, improving temporal consistency. This focus on effect of outlier handling in approach 2. When approach 1 is applied alone, we can see separation artifacts around gone better. But with approach 2 added, the separation was noticeably suppressed. On another stage sequence, we can see a similar trend. So approach 2 make approach 1 more reliable from unwanted deformation. While our method improve coding efficiency and visual quality, we also add complexity. Minor encoder overhead was minor, but at the decoder side, the runtime significantly increased, especially when approach 2 is applied. This mainly comes from two factors: more complex subdivision scheme in approach 1 and vertex classification in approach 2. We did not use any acceleration or optimization techniques, indicating considerable room for further improvement. Looking ahead, we plan to reduce this complexity, and we also plan to explore automatic parameter selection so that encoder can adjust iteration count or edge range threshold on system-aware or content-aware way. To wrap up, we addressed the two gaps in VDMC subdivision. Approach 1 enables a flexible scheme selection across LODs, while approach 2 safeguards the pressure region. We can see consistent speed rate gain and perceptual quality improvement based on MPEG sequence test result, or achieved with minimal pipeline change, indicating that our method could align well with ongoing standardization efforts. Main limitation is decoder complexity, so looking ahead, we plan to reduce the decoder cost and automate the parameter for real-time deployment. Thank you.
Yeah, thank you so much. Thank you. Maybe we can invite one quick question. Any question? If not, how about this? Maybe I think that if any question, they can just come to you after this session. Will that be okay? Yeah. Okay.
Thank you for introduction. Hello everyone, I'm Ayaka Yasunaga from Keio University in Japan. Today I'm going to present our work, IntelliCap, Intelligent Guidance for Consistent View Sampling. This is a collaborative work with University of Stuttgart in Germany. New method for novel view synthesis from images has made great progress. The underlying scene representation are optimized using differentiable rendering. The key requirement for differentiation is uniform and dense sampling of the input view, so that a reliable estimation of gradient can be performed. However, in practice, it's hard for humans to capture such ideal images. They may lack the skill, time, or understanding of how to take the right pictures. This problem gets worse as the scene size increases. Therefore, the core challenge is how to effectively design view sampling strategy or for novel view synthesis that requires fewer merge view images. Augmented reality can visually indicate where to operate a camera and collect image sample. Popular forms of annotation include 3D axis, 2D plane, and semi-sphere surround the target area. This method requires the photographing task as a data collection task. For example, when using a smartphone, 3D annotation appears on the camera screen. The user moves the phone to align to hit these annotations. Once the phone is in the right position, it automatically takes a photo and moves to the next annotation. Existing approach aims at capturing only a single target object or a small area in front of the operator. Therefore, solutions that scale to larger scene or open area are lacking. File view-dependent effect must be comprehensively captured. The data collection task should be completed in a practical time frame. Therefore, the sampled area must be prioritized. For example, glass bottles or leafy plants demand denser sampling than simple planar objects like desks. Novice users often don't know how too many photos are enough and lack a visual guidance system to show when sampling is complete or which area need more attention. However, scoring into visual object during photo capture remains a challenge. To tackle these technical challenges, we propose progress visual indicator using 3D mesh and Sophia proxy, and area-based scoring of detected objects and their categories. Users walk freely through our environment, while our system performs 3D reconstruction to evaluate spatial coverage. Meanwhile, the system detects objects and generates spherical proxy to attract the user attention. As user continues scanning, new objects may be found, spawning additional proxy to prompt denser view sampling. Once all highlighted visualizations disappear, the user can consider the view sampling process complete. I'll then move on to the proposed method. We developed a system that captures image at a fixed interval. To guide the user, the system provides two types of visual highlights. First, we highlight regions that have not yet been reconstructed based on the current step of the 3D reconstruction. For simplicity and implementation performance, we utilize a smartphone native scene meshing API, AR-Core or AR-Kit. Further mesh proxy supports spatial coverage when does not account for angular sampling. User may miss critical photometric details such as specular reflection or transparency. To address this, we detect only objects that need denser sampling. Only for this, we generate 3D Sophia proxies. To generate the 3D Sophia, we use Detectron 2 to detect object segments and their categories from RGB image, and project them into real-world space as spheres. We use a LLM with a custom prompt template to evaluate the visual characteristics of detected objects and prioritize them accordingly. High score objects are anchored in the 3D scene. Furthermore, to effectively capture image around 3D Sophia, we introduce three key components. First, to prevent confusion about occluded area, we avoid overlap between sphere and sphere scene elements. This helps users know they don't need to capture behind occluders such as walls. The alpha value of each sphere is dynamically adjusted based on the its depth relationship with surround scene elements. If the sphere is behind something, so is it hidden? Additionally, to allow the user to approach the sphere during the sampling, spheres are visualized only when they fall within the valid distance range. The full sphere appears when it occupies more than 20% of the camera's field of view. In practice, as the number of the spheres increases, the workload captured the workload for capturing become higher. So we aim to reduce the number of the sphere by intelligent merging. Initially, a collision check is performed between the sphere. If one sphere is free inside another, we just remove the smaller one. Otherwise, the two spheres are merged into a new sphere. We conducted a user study to evaluate our system to turn off the resultant view synthesis quality and usability at different scene scales. We designed a repeated method within subject study. We compare our approach with two baseline approaches. One baseline displays only a video stream, and the other visualizes spatial coverage. We collected 12 participants, and to increase visual complexity, we intensity against the object with reflective and transparent materials. The object highlighted with the red line have a high potential to be abstracted as spherical proxies. This slide shows the result of the 3D Gaussian splatting and fact view synthesis. Our method outperformed the baseline in all image quality metrics. Ours achieved the highest performance, followed by the only spatial coverage SC and no visualization NV. This presents qualitative comparison of the 3D Gaussian splatting result. Our approach generates high quality, consistent reconstruction across the entire scene. It also effectively captures challenging aspects, such as specular reflection and transparency, which baseline method often miss. To evaluate the usability, we collect SUS, NASA TLX, satisfaction, and the number of the collected images. Satisfaction measures evaluation on a 7-point scale between total agree and disagree. Total disagree to total agree. With the question, I am satisfied with the scene scanning per method. Spatial coverage SC received higher SUS score compared to the no visualization NV. No significant difference was observed between ours and SC. We believe that the extra spherical proxy in ours may have increased the cognitive load, explaining the slightly lower SUS scores. Similar trends were observed in NASA TLX and satisfaction scores. Interestingly, participants using NV and ours collected a similar number of the images, while SC resulted in significantly fewer captures. As I mentioned in the previous slide, ours achieved the best view synthesis performance. This suggests that it guided user to additional viewpoint that SC failed to capture. It also demonstrates a more efficient view sampling than NV. In conclusion, we propose a novel view sampling approach for high-quality view synthesis, which supports multiple scale and complex scenes. Experiment results demonstrate that this strategy leads to consistent rendering performance and effective task performance. We also identified limitations and interesting direction for the future research. For example, to improve efficiency and user engagement during the build sample process. Multimodal feedback can help guide that and motivate users. Thank you for your attention.
Thank you so much. Any question from the floor? Okay, how about I actually have one question. I noted that large language model is used in your research, right? LLM, right? From my experience working with LM, normally, first of all, it need to be deployed on a big server, okay? And also the speed is not that fast. But I saw from your video, it looks like everything is done very fast in real time. So just want to check with you, for your large language model LM, what is it?
Yes.
Yeah.
So about LLM, so
Okay.
We create the prompt template and ask the score according to the objective categories. So this is the prompt template.
Okay.
So this parameter includes geometric complexity and texture complexity and size, specularity, and transparency.
All right.
Yeah.
Okay. All right. I think that makes sense. Yeah. Thank you so much. Thank you. Okay.